Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started. It's a pleasure for me to welcome Lenore Zuk from University of Chicago, Illinois, and I will tell you a little bit about how I met Lenore, because it was an interesting encounter. I hadn't worked very long at Microsoft Research when someone came up to me at a conference and said, "Oh, you work at Microsoft Research. I'm so happy to see you." That was the first time someone ever came to me saying that. At that time, people weren't really used to Microsoft Research. It turned out, though, that what she had in mind was that I should take a wireless card to Andy Gordon, who'd forgotten it in Copenhagen. So, but then today she's here to talk about one of many projects that she's been involved in. She's probably known for having put the past into temporal logic. She's been doing work on distributed protocols, security protocols, but also on translation validation of optimizing compilers.
Thanks. Talking about your introduction, I guess when I started talking about the past in temporal logic, I had the slide that the title was, "Why Should We Be Ashamed of the Past?" So anyway, I've got this. No, this is not the thing that monitors. Oh, okay, I'm sorry, this. Okay, this is what I'm looking for. This project is basically a project that is done in the Access group at NYU. Access is advanced computer systems. As some of my colleagues at NYU would like to say, my office moved about 1,000 kilometers west. But this is basically still an NYU project, and let me correct Jacob, I'm not in the University of Chicago, Illinois, but I'm at the University of Illinois at Chicago, which is actually a different university. And it is. Okay, the outline of the talk is the usual. I'm going to talk a bit about the past and what led us into this project. About the present is what we have right now. And about the future, and some of the future has already been put in the present. It all started in one of the European projects, SACRES, that is safety critical embedded systems. It had 3 types of participants: industrial participants, which were British Aerospace, Siemens, and SNECMA, 2 vendors, and technology, which was INRIA office in Germany and the Weizmann Institute. And their goal was to develop methodology and tool set for critical real-time embedded systems. They started from specification, which was given either in SILDEX or Signal, and state charts, and they translated it into executables in C on Ada. The part that they ended up being focused in SACRES with the Signal to C. Their premise at the time was that all the verification and validation happens at the higher level, and once you've got a correct specification, it's being translated without further ado into C, with the hope that whatever was shown to be true at the higher level is true at the lower level by the sheer virtue of the translation. However, they soon noticed that since they need to certify every component, they also need to certify the automatic code validation, in that case from Signal to C. And of course that is really difficult. It's expensive, and also the translation, the compiler that translated the Signal to C kept undergoing changes, and the nature of verification is that once you verify it, you have to freeze it if you still want it to be correct. So that didn't seem to be a good idea. So then they had the idea that rather than verifying the translator itself, they can verify each of the translation. So this is once you translate a code into C, you just verify the translation. The advantages would be that the evolution of the translator doesn't need to be frozen after the verification because you do the verification per case. It's going to be cheaper, and it also is going to offer an independent cross-check to the compiler. The drawback that it does add a constant runtime, but it was deemed to be justifiable. Consequently, they developed a tool known as CVT, the code validation tool, that automatically verifies signal to C translations. And they had some good experiences in terms of runtime so that it would not be too expensive. But there were two main assumptions that made that possible. In the case of signal to C, there is basically, it's a synchronized, the computation proceeds in locksteps. There is a synchronized thing, there is a main loop, and in each point and in each iteration, only one instruction gets performed. So that makes the translation very simple. There is really one-to-one mapping between instruction in the source code and instruction in the target code. The other thing is that there's an extremely limited set of optimizations. And it is so limited that I haven't been able to figure out one single optimization that happens there. They could use the theory of uninterpreted functions, and they had a really nice algorithm that made the CVT tool so efficient. So that really taught us that it can be done, but perhaps we can open the framework to a bit more. So we came up with sort of a more pretentious goal, and that is to guarantee the correct functioning of optimizing compilers. And we were targeting towards EPIC architecture, basically for very, very mundane reason. We're at that time, that was at NYU. NYU still had the trimaran project there, and we started thinking about the trimaran. We did not know the trimaran was actually the name trimaran because there were 3 groups working on it. And it ended up that the group that actually developed the front end at that point disappeared. So we had to give up the trimaran because we didn't have much access to the front end. But that's where it started. We figured out that if we manage to do it, it actually is good for several things. It's good for safety critical applications, because then you can really certify everything. It's going to be good for compilation into Silicon, where the cost of translation error is prohibitive. And we want to show that whatever correctness and verification that is done is a high level does hold at the low level and is not impaired by the translation. As I said, we wanted to start on trimaran. We actually ended up starting on the SGI Pro 64, and then they closed sourced it. So we switched to the Intel Open Research Compiler, the Intel ORC. And that compiles for both C and Fortran. It has 3 levels of optimization. It starts with loop optimizations, goes to classical global optimization, known as a Red Dragon optimization, and then does machine-dependent optimizations. Currently, we have 2 tools that are listed in the order that we developed them. We have for global optimization SPTV. It actually stands for structure preserving translation validation, and LoopTV, which is we're looking at reordering, not general optimization, just at reordering transformations and loops. Okay, let me give you an idea of the type of stuff that we want to do. So here is a program that finds the integer square root of 500. And this is how it looks after typical global optimizations. There is constant propagation, strength reduction. What?
What does it do?
The integer square root of 500. You may find a simpler program that does it, but I agree that an ideal optimizer would do a bit more. This is actually taken from a real, to really rerun this and saw how the optimized code looked like. So we look at basic blocks, which are single entry, single exit blocks. And So we have this as a source and this as the target. And we would like to build automatically verification conditions such that if the verification conditions hold, then this translation is correct. So what does it mean for a translation to be correct? We say, so what we do is basically best viewed in this diagram. We have a source program that by the optimizing compiler to get translated to a target program. We in effect look at intermediate representation to intermediate representation translations, IR to IR. We have semantics for the source and we have semantics for the target. And then we establish refinement relation in between the target and the source. So once we establish that, this pointer doesn't really, okay. Once we establish that, we can show that we have, that the target really translates the source. That is, we are looking at deterministic programs, deterministic transition systems. We translate everything into transition systems. And we show that for every pair of target and source that start in compatible initial states that have the same input, either they both diverge or they both terminate. And if they both terminate, they terminate with the values of with the same values of variables at select point. The same value means that there is a correspondence that we can define. So we started with structure preserving optimizations. What are structure preserving? Actually, it's a bit of a misnomer. Structure preserving, for those of you from the verification discipline, means that we can establish Floyd rules to show the correspondence. That is, we can choose control points, and we can choose on the control points mapping in between the data, and we can show that this is preserved. Structure modifying is anything else. So structure preserving does not mean literally structure preserving. It does allow for things like loop enrolling and loop invariant code motion, dead code elimination. It does allow for some changes in the structure, but basically the control graph remains isomorphic. And structure modifying is we cannot apply Floyd type of rules. And that includes most of the loop optimizations. Reordering, tiling, reversal, that type of stuff. This is what we'd like to do. So what we'd like to do is to take the code, the source code in C or Fortran, forget what's written here. We'd like to take the assembly level and to show that they're the same. Okay. We're not doing that. We're far from doing that. What's happening in the middle, there's a front end, it gets translated to IR, it goes to several rounds of loop optimizations, then to several rounds of global optimizations, then to machine-dependent optimizations, then it gets through the code generator translated to assembly. And this is all done in the compiler. So bear this picture in mind and know what it is that we don't do. What we do rather looks like this. We only look at the things at the IR level. We don't deal with the source or the assembly. And we, after the loop optimization, we take the source, before the loop optimization, the target. We take several other things, information that we need that I'll elaborate on later. We send it to the loop TV for verification. Then we look at the global optimizations. Here we actually do something cleaner. We really take the IR before any global optimizations and the target after all global optimizations and feed it into our structure preserving translation validator tool. That builds the verification conditions that are sent to CBC Lite. CBC Lite was actually specially outfitted. Clark Barrett works with us, and he made CBC Lite work for us and be very efficient at checking our verification condition. And then we get either that it's valid or we get a counterexample.
So CBC Lite is a theorem improvement?
Yes. So as I mentioned, for the structure preserving optimizations, we do simulation, relation, And I mentioned that it actually includes some of the non-structure preserving optimization. Basically, our proof rule, we have one proof rule that we use. It's called validate. And we take the transition system of the source and target. For each of them, we establish control abstraction from some of the target's basic blocks into some of the source's basic blocks. The basic block that we choose to map we refer to as a cut point set, and following the traditional definition of a cut point set, it includes the entry point, the exit point, and at least one basic block from each loop. Then we establish data abstraction that maps abstract variables into guarded expressions over concrete variables. Abstract variables are the source variables. I actually am trying to some degree of success to denote the source as the abstract in blue and the target of concrete in green. And the reason these are guarded expressions is exactly for the points where there's code motion. So in case of code motion, we cannot have a direct mapping between expressing source variables as a function of target variables, and we use guarded expressions. That may be our main claim of innovation. This is probably where the main power of our tool lies, is in automatically generating invariant assertions in each of the basic blocks. And that allows us to specify the verification condition. And the verification condition would basically say that if for every simple path between two control points, if the data mapping held before, then if we take the step in source and target, then the data mapping would hold. And actually, if the data mapping held and the invariant held, then the new data mapping will hold and the invariant will hold. I'll give an example, but before that, Chaz had a question.
I was under the impression that compilers usually don't change the data representation. So you would need data abstraction mapping only if the data representation changes, right? In doing the optimization? What kind of...
what do you mean by data representation? If we
what I meant was...
back to the example, for example, here. So, for example, what is n in the target?
Oh, so there is no n in the target. I missed that. Actually.
Yeah, there is no n. And I guess you have everything else, but you want to express every source variable as a function of the target variables.
Oh, so you were able to get rid of n by doing a constant propagation?
I did not do it. Yes.
But is there anything, that's pretty, is there anything else? Anything else?
Yeah, you could
actually... It's non-trivial, this is pretty trivial, right?
Right, but look at look at loop invariant co-motion. So when you have that, then how do you define, suppose that you carried some code out of the loop, right? Then you want to map the source value to the target value at the first entrance of the loop. And you kind of lost it because you carried it out.
I see, okay.
So there are all those things that can happen.
Isn't t a new variable also in this example?
T is a new variable, but we are concerned with mapping source variables into target variables.
Okay.
We want to express the source variable. So when we do the control mapping, we map target to source. When we do the data mapping, we map source to target. Okay, let's look back at this example. So this is the example we had. In that case, the cut point set is very trivial because the target only has a source, like a single entry, the entry and exit, and it has only one basic block in the loop. So it's clear that all these 3 points have to be the cut point set. Now we have to map it into the source, and that's the way we do it. I can say that generally we try to look at the source at the last statement of the loop. That seems to work better. So here is the control mapping. Next we need to do the data mapping, which in this case is trivial. And after that we need to compute the invariant. And the only interesting invariant is the invariant on the target B1. And this is because of the strength reduction. So we have the t equals 2y. And from that, we build a verification condition. So the verification condition would say that here is one example of a verification condition, and this verification condition is for this path. We need to do it for every simple path, which will be for the B0 to B1, B1 to B1, and B1 to B2. Just to remind you, a simple path is a path between two control points that doesn't have any intermediate control point. So there are three simple paths here. For the 0 to 1 path, we have that this is the initial data mapping, and this is the transition on the concrete. This is the concrete transition in the target. This is a concrete transition in the source that maps to it. Notice that in the target, we went from here to here unconditionally. In the source, we need to look at on this path. This is the path that we're mapping. And in this path, we're only taking if W is less or equal to N. So we have this condition. Then if all this holds, we want to show that the new data mapping holds on the prime variables, that is the variables after the transition, and that the invariant assertion holds at B1 after the transition. So we developed such verification condition for each basic path, and we send those verification conditions to CBC Lite. So this is indeed what our tool does. We're looking at verification conditions from the IR used in the ORC compiler, and actually lucky for us in the SGI compiler, so whatever we had on the SGI we can just take over was real. That's just the language of the intermediate representation. And our tool takes this intermediate representation, translates it into the transition system model, and produces a CBC Lite ready verification condition. It has the following parts. It's got a parser that translates the IR code into the basic blocks, the cut point set computation, basic path computation, the transition relation, because we need to compute the transitional relation, which is generalized transition relation on every path, the invariant computation, and the data mapping, and from that we obtain the verification condition. So this actually had been very successful on proving things that only have global optimizations and no loops, and then we wanted to venture into the loops, and we had a problem because all the simulation-based rules assume that the source and target have basically the same structure and the same structure of loops. If we have anything that actually rearranges, reorders the execution of loops, that doesn't hold anymore. Because if you remember in the cut point, we need to cut every loop once. So we don't have any more natural mapping of the data. So we can't use such refinement rules. And we're just restricting, as I said, to reordering transformation that change the order of execution statement, but it doesn't add or delete any statement. So that's a restricted sort of loop optimization, and still includes a wide set of them: loop reversal, interchange, tiling, distribution, fusion. Even we can throw in skewing and unrolling and peeling into here, even though they really don't change the order of execution. But whatever we do, of course, holds if the order of execution doesn't change. Oh, I wrote that. OK. So here is a loop interchange. So loop interchange, we have a doubly nested loop, and all we do is change the order of iterations. Why would we do that? For example, we have a better cache performance if we're storing a matrix in a column major. And also, once we do this, then this becomes loop invariant. And we can compute it only once, which is not the case here. So there are some performance considerations of doing this reversal, and modern compilers, this interchange and modern compilers would do that. Compilers use a lot of techniques in order to determine when those things can happen. They use the flow, all the dependent analysis. We don't need to do that. Our goal is not to produce optimizations. Our goal is just to show that they're correct. So we can be much dumber than compilers are. So we're just use logical conditions that capture them all. We needed to come up with sort of a generic loop framework. So what we looked as a loop to be, a general loop to be of the order that we have, let's say that we have the iteration space, script I, the vector space on which the loop iterates, and we have some ordering, total ordering, which is the order of iteration. So the total ordering is denoted by this, and this is the iteration space. So this is just a generic presentation of a loop. For example, in this loop interchange that I showed before, the iteration space is all the pairs I1, I2, in the order that I1 is between 2 and n, and I2 is between 2 and m. We're using the usual lexicographical order, and the loop body is just the statement that we have in the loop. So it's kind of trivial. What does a reordering transformation do? A reordering transformation transfers the vector space into another vector space, and the total ordering, the original total ordering, into a different total ordering. So this is a new vector space, and this is a new ordering. Now, in terms of the loop body, what the loop body in the transformed loop is assume that we have some bijection between the new iteration space to the old iteration space. What the loop body does, in each iteration, it performs the loop body with respect to an iteration of the original vector space. Let me explain if this doesn't make much sense. Let's think that in tiling we take a nesting 2 and we transform it to nesting 4. But in each statement in the tiling, in each of the body loops, really what you have left is a statement that refers only to 2 indices, not to 4. So we may change, the transformation may change the iteration space, but it works on things that are basically in the vector space of the original vector space. So we change the domain from script I to script j, and the name of the loop indices changes from boldface I to boldface j. And we may need this additional linear transformation, changing a body of the source into a body of the target. So here is an example. In this transformation, it's very clear what we looked at the initial vector space, the final vector space, it's just that reordered. We still have the lexicographical order, but when we are going to execute an iteration with J1 and J2 in the source, we actually execute it on reversed indices. So our f function would just do the reversal. We have one generic rule for loop reordering transformation. And this is assuming we know the f. So suppose you have f and you show that it's a bijection. And the idea is that the source and the target should actually execute the same instances of the loop's body, possibly in a different order. Then, and this is a crucial point, when would a reordering transformation would not be correct? A reordering transformation would not be correct if we had something executing in one order in the source and that order being flipped in the target. So the loop body with I1 was executed for the loop body with I2 in the source, but in the target, we're actually executing the loop body with I2 before we're executing the loop body with I1. So this is our danger spot. And if that doesn't yield the same result, then we're in trouble. And that all the independent analysis actually makes sure. So we're looking at every iteration such that I1 was executed before I2 in the source, yet in the target, I2 was executed before I1. And for each of them, we showed that it really doesn't matter in which order you execute those statements, those loop bodies. And if we manage to show that, then we can show that the reordering transformation was correct. So in a way, in a sense, all it takes is to identify this f. So here is back to the example. We know what f and we know what the inverse of f is, and this is obviously bijection. And next thing we have to check is that with every iteration that gets reordered, it doesn't really matter in which order they're performed. Well, when does it, in interchange, when do we have reordering? We have reordering that in the going by rows, some iteration was executed before it was when we go by the columns. So this is the case. When we execute I1 when we go by rows, I1, I2 is executed before I1 prime, I2 prime. But if we go by columns, then the order reverses. So we need to show that for any two input vectors, any two assignments of the input I1, I2, and I1 prime, I2 prime, if I1 is less than I1 prime and I2 prime is less than I2, then the loop bodies, the ordering of the loop bodies doesn't matter. So that all it amounts to showing in this loop reverse and loop interchange. Yeah.
So this rule isn't strong enough for all reordering optimizations, right? Is that correct?
I don't know. I mean, it is, if you specify f.
But might there not be cases where you need to think about moving pairs of iterations around, and you can't always have this pairwise reordering property? There might be more dependencies than you might be able to move blocks of iterations and preserve the right properties, but move single iterations only, you don't get the right relationship.
So what you're asking, whether the rule can cover it?
Yeah.
If the transformation is correct, the rule will show that it is correct. Right, when you do a reordering transformation, then you have a bijection. The mapping in the source and the mapping in the target. All the rule says go pairwise, and if you find something that the order was flipped in the target, show that it doesn't matter in which order it was executed.
But might there not be some state dependencies where looking at the individual effects of the iterations, they don't actually have the same effect, but due to some state that was around, given the way you reordered it, they do.
That may happen. So maybe the counterexample that you produce, right? Because if it's not shown, then you get a counterexample.
But when it's script, you still have sound optimization.
For particular data, you can. But I would argue that I don't think it's likely that a compiler would come up with it.
Okay.
Right? A compiler would take a very conservative view and would not allow lots of knowledge about the data to determine the optimization. So, yes?
I guess it's maybe worthwhile pointing out, at least as I understand it, is that this is just one example of a rule for a particular kind of optimization. Now, if you were to write, for example, a very complicated smart compiler, you as a compiler writer might be the person who would want to come up with a validation rule.
Yeah, but I think that...
Right? You could tailor that, too. I mean, if you do really weird things, you could still maybe find a rule that would validate it. Okay. And I mean, you would probably have some sort of rule in your head when you design your compiler, because you have some idea that the compiler is producing the equivalent code.
No, I thought the question had to do more with a particular case where something happened that in the general case it would not work. Did I get it wrong?
No, I mean, so you're reasoning about the effects of the loop body as a function, but the loop body doesn't always have local effects. It can depend on previous iterations. So that's why it seems like it's not a general enough rule.
Do you have any optimization in mind that you think doesn't get covered?
Not at the moment, but it seems like there could be one. I'd have to think about it.
Okay, I'd be interested to see one, because I do think it would get covered if it's something that can be generated automatically.
Okay.
I thought you meant but just particular cases. Okay, so going back to that example, the only thing that matters is that you could actually generate a CVC condition, a verification condition, and send it, and that's how it looks like, and we send it to CVC Lite. and which will tell us whether it's correct or not. Okay. But actually, to apply this rule, we need the F function. Now, I know many of you actually develop compilers and know the optimizations, what we're using. But when we started doing it, we had this very ideal picture that we don't have the compiler, that we want, as external observers, get the IR before, get the IR after, and show that they're the same, with no access to the compiler itself. Now, we're working on the ORC compiler, and it was clear that if we could only find those, if we only know which transformation happened, then we'll be able to verify it. But what happens if we don't know which transformation happened? And so luckily and mistakenly, we stumbled upon a file called .l. And .l has the list of all the loop optimizations that ORC tries to do and what's successful and what's not. Now, my personal feeling is that somebody used it for debugging and forgot to erase it. And maybe in some later release it won't appear, but at this point there is a .l file, and we're very happy to use it. And the .l file tells us what happened. However, it's not that nice. It's very difficult to stop the ORC after a single optimization. And actually, it's impossible. We really tried. We once tried to stop it after dead code elimination. Just let it do dead code elimination, and it eliminated all the code. So the after was an empty program. And we gave up on being too controlling over it. So what we do is so what it really does, it does loop optimizations. So it tells you, I did peeling, I did fusion, I did unrolling for 2 iterations. It gives you all this thing, but it gives you the whole history of that. So a bunch of optimizations, and then what it doesn't tell you, and I did a bunch of global optimization. It doesn't give you just, we'd like to have, okay, you did reordering transformation, just do the single reordering and just stop and let us verify it now. It doesn't do it. So what we do is that we say, okay, we'll look at all this loop reordering transformation that happened. We actually look at it one at a time. Let's just assume that one happens. We can easily extend it to several. Then we cannot stop it. We cannot look at the IR after, because we don't have the IR after a single loop optimization. We have the IR after the loop optimization and then some global optimization. So, but we want just to verify the loop optimization. So the way we do it is we synthesize. The ORC tells us, I did interchange. So we synthesize how an interchange should look like had he done it, which he may have done, we don't know. So we get the synthesized IR. Then we'll use our loop TV to show that, and we use the fact that we know which function was used. We use this .l file to tell us what was used. It says, oh, you had interchange, and then we use our F library and tells us in interchange, F of I1, I2 is I2, I1. We synthesize this loop, and we check that this was OK. After that, when we know that this was OK, we take our synthesized loop, our synthesized code, and compare it with the real code, and send it to a structure preserver, preserving translation validation. So we have to go to this synthesize step to compare it with. Okay, currently our F library has all those things. We can easily add more. So if a compiler has more, we can easily add more. Then if we have a bunch of them, as I said, it does peeling and then fusion and then alignment and all those things. If those things happen, we actually go and synthesize them one by the other and check the validity of each. We're still using this .l file that tells us which optimizations happen, and as I mentioned, we're not happy with it. The main reason I'm not happy with it, I'm not sure it will exist for long. I don't.
Isn't that just an artifact of ORC? I mean, shouldn't anybody who really wants to do this seriously be willing to instrument their compiler?
Suppose you want to use translation validation on a compiler that is proprietary information. They don't give it to you. See, for the structure preserving optimization, we don't base anything on which optimizations really happen. We look at the source before all the global optimization, the target after all the global optimizations, show that they're the same, without any information from the compiler.
I still think it's reasonable for the compiler to give you information.
I think so too, and I think the more information we get from compilers, the stronger tools we can build to do this type of work.
I mean, for a number of, for some optimizations, synthesizing any optimizations involving loop invariants might be very difficult to prove correct in some situations. If the loop invariant is suitably complex, you could conceive of that. So it's, you know, if you look at what George Necula did, for example, people had to provide loop invariants, and the compiler had to synthesize loop invariants in some places. So.
What he did, you mean with the translation validation?
Yes.
He didn't deal with loops. He didn't do loops at all.
Okay. Well, maybe I got
There was a reason. So he didn't do loops, and actually, for example, he can't do the code motion stuff. The loop invariant code motion he can't do. So, yeah.
Could I ask, so if there's a mistake in that .l file that you're using, does that blow away the validity of your translation check?
Okay. Here's the next slide. So as I said, we are not, I'm not saying we are not, it's actually I'm not. Everybody's arguing with me that that's legal. So we needed to get rid of it. I don't like getting the information from the compiler if it's not official information from the compiler. I would like it if somewhere they would tell me, you know, there is a .l file and it tells you, and this is the meaning of the .l file, and not something that we just found by mistake. So we use a bunch of heuristics to determine actually which transformation happened. And we can determine, since this is reordering transformations, back goes to the thing is that the compiler does only so many things. And we can figure out by the loop structure, by the iteration bounds, and we can try to reconstruct what actually happened. And we've done it to actually so far success. So at this point, maybe we don't have very complicated example. I mean, I will not be surprised if we fail. I will not be surprised if that doesn't work for every example. And we actually had some interesting things that our heuristic generated actually different order optimization that actually what happened. But the point is, if we prove that what we have is correct, no matter what led to it.
That's very strange.
No, it's not strange.
And did you try to over-approximate instead of a rejection in math, math I to several possible values?
No. When we started, we're trying to construct a very general loop framework. And after a year, we gave up. And we decided we'd deal with one optimization at a time. So what you're saying is more trying to come with a general framework?
No, it's, again, only for one translation. But when you guess F, you don't guess a rejection, but guess something that is more general.
But the proof will say that I have to show that it's a rejection for it to be a reordering.
Okay, so
Maybe there is
completely different.
Yeah, so then maybe for a different proof rule. So we also worked a bit using this framework for speculative optimizations in which the validity of the optimization only depends on runtime. For example, let's look at this interchange, and what's different here is the K. And this optimization actually is only going to be correct if K is non-negative. Because otherwise, we're going to have a counterexample. So this would look like a correct speculative optimization of that. And that requires runtime tests. So what we do under the same framework is find the conditions under the validation fails, do the runtime test, and during the run, send it to CBC Lite to check the runtime tests. We actually, so we have that in our framework. We actually have a tool. Itai, can you give us the, Itai knows the URL of the tool. Of the translation validation stuff, because I don't.
It's somewhere under our website. I don't remember exactly.
Okay.
Sorry.
Some people know the URL. So there's the things that are in the tool as we have it on the web, and there are things that are not there. So some of the things that I said we don't do, we actually do them, but they're not in the tool right now. They're not being tested. So what we don't have anywhere is, almost anywhere, is dealing with exceptions. So what I mean, some exceptions may be true, may be introduced by the translator. So my generic example is, suppose that I have the source says read A, and the target says some temporary gets 1/0, read A. So our tool would say that these two are equivalent. Right. And we don't deal with exceptions, but it's not that we can't deal with them. It's a choice. We can actually deal with them. We can add for every instruction that can generate an exception, we could actually add the condition that generates the exception and check for it. Now, in fact, we do it. I work with Intel, and we do backward compatibility of microcode. And when you work with microcode, you cannot gloss over exceptions. They have to be treated to a great level of detail. It's when you have an exception, there are some side effects, some effects on the environment. You have to show two microcode flows are going to be equivalent only if when they have an exception, they have the same exception and the same effect and the same everything. So, and the translation validation framework works for it. So when I say we do not check exceptions, this we do not check in the tool. But the framework is strong enough to check exceptions and to deal with that. That will add an enormous complexity to the tool. For what we use it's not necessary. When you do microcode, it is necessary. Our ability to check algebraic simplification is only as good as our theorem prover. Again, there could be code that are equivalent, but they have different algebraic specifications that we cannot check in the theorem prover. We'll say that they're not the same. So we will produce false negatives. Again, we do not handle pointers and aliasing. We do not handle pointers and aliasing in the web version of the tool. We now have the framework to handle pointers and aliasing, and it's almost fully debugged. Procedures. We do not handle procedures. I'm talking about inter-procedure optimization. It's almost following our loop story. We try to come up with a general framework to do all procedures in one nice proof rule. We gave up. We're now doing one procedural optimization after another. So inlining, tail recursion have been dealt with, but with more, and nothing has been incorporated into the tool. Okay, this is the end almost. The related work, there is lots of work on verification of compilers. Verification of compilers has been done for years. More recent, there is work on verification of optimizations. That is, the general framework is to express the optimizations using, because most reminiscent of what Bernard Stefan did with expressing, using temporal logic to express the data flow conditions, and showing, working with the compiler and showing each optimization, showing that it is correct. Then there is work of verification of the properties of optimizations, and Javier Rival, Leonecula, and Taylor was here. Then there is a translation validation where we started. This is the CVT tool that I told you about. And also George Nekula did the translation validation for the GCC. And as he described it, he did it in 6 months, 5 years ago, and never worked on it since. So, the conclusion is that we can do translation validation, and we can do challenging optimization. It's conceivable that our current tools or current proof rules don't deal even with the scope optimization they claim to deal with. One can come up with a new global optimization that may not be covered by our tool, by our proof rule. Fine, we'll need to extend the proof rule. It happened before. And there may be new reordering transformation that we're not dealing with. So that I do not consider that a major weakness. I think the approach still works, and sometimes it takes some tweaking with the proof rules to make it catch some more. Currently, what we're doing is we want to test the tool on really large examples. So we made it to about 1,000 lines, but we want to do more. It's hard with the fact that we don't have procedures and we haven't quite done all the pointer stuff into the tool. For the loop part, we want to incorporate the heuristics. We actually did it. As I said, the aliasing in the inter-procedure optimization, we should incorporate it in the tool. And we should really move on to machine optimizations. And instruction scheduling is the main hurdle. We have to figure out how to deal with it. That is what I consider the main hurdle. We want to work on code generation. We want to verify the code generation. We spent some work on it, and I think our conclusion that doing it for the ORC is futile. It's hopeless. And the reason is, if you just look at the instruction set of the ORC assembler, you'll understand why it's so hopeless. And if they need about, I think, somewhere between 400 and 600 pages to describe it. And it's just really strange things there. If anybody's interested, I can tell you some of the experiences of trying to do it. It's just not a very clean, it's a very ad hoc, case-by-case translation. If we want to automatically verify it, we'll have basically to follow case by case. So it will be nice to find a good code generation that can be cleanly verified and do it for that. We want to develop a self-certifying compiler. Well, I mean, between all those tools we developed, we have everything to do our own compilation. And then we can do, since we have all the validation tools, we can do totally self-certified compiler. We want to apply this approach to different translation. Mainly, we are concerned now with translations from, let's say, system Verilog to Verilog. We want to work to apply this also to visual IDEs. And as usual, looking for other venues for the approach. As I said, we're doing it for microcode, but we're looking for other partners and ways to apply it to different things. Thank you. Itai.
It's in Access/TV under the NYU website. I don't know.
Access/TV.
The marker there? I don't know if you can.
Where do I have access?
No. I mean, whether you can write it on the board.
Oh, I see. Access.
Access to the C. No,
TV. Sorry. Oh, TLV is something else that we have there. Okay. Yes.
Can you check procedure inlining?
We think we do. I told you, it hasn't been fully tested, but it's been implemented. But this is all kinds of the tests on the side that we do. We don't feel comfortable enough to say that we have it and to bring it into the tool that is on the web.
You said we needed some special support by CVC Lite. What might that have been?
Well, Clark just tinkered with it and looked at the exactly verification condition that we're getting. what they were producing. So we are tailoring our verification conditions to be easily checkable.
But your verification conditions just include propositional, Boolean operators, arithmetic, and uninterpreted function symbols, right? Do you have quantifiers, for example?
Actually, the original proof did have quantifiers. And we played with it to change it, to make it simpler for CVC.
Did you ever try simplifying the simplify theorem prover?
No.
See if it performs better than CVC?
No, we did ICS.
Yeah.
And for various reasons, we decided to move to CVC.
Well, with Clark.
Exactly. That was one of them, yeah.
You mentioned that the CVC Lite gives you a counter example. What kind of counter example does it write?
What do you mean, what kind of counter example?
So, in one of the slides, you had that if CVC Lite fails to prove,
Then it shows you an assignment for which doesn't work. For example, for the loop example, it shows you the iteration instantiation for which it fails. Values for the iteration, yeah, for the iteration.
You said you now handle pointers. So what did you change? You model, the heap or all of memory, or what do you do? Or do you do some pointer analysis on the?
We do pointer analysis on the program.
Wow. Uh-huh.
Oh, yeah.
Probably in the easier way.
It's been sort of a long way. There is actually, the main developer of this is Yifang, who's going to be working here starting September, October. And this is a condition that she graduates, and this will be done. So this is my condition to letting her get her PhD. So had she stayed for a postdoc with me, she would have done the procedures too, but.
No more questions? Thank the speaker.